So we're now going to talk about the TaskGang framework. We actually covered this in an earlier video series on the image TaskGang, but I didn't have a bunch of cool slides like I've got now. And I think this may give a better high-level view of what the framework does. So we're going to talk about the different methods that are defined by the TaskGang framework and discuss their role in the overall capabilities it provides. So again, keep in mind that this framework is used to spawn and run a gang of tasks, where gang is used in a very loving way. These are tasks that like to work together. And a task is basically a command that can execute in a background thread. And we'll see that there are different ways of implementing those tasks using different types of thread pools or virtual threading mechanisms that are part of modern Java. The purpose of this framework is to concurrently process input from a generic list of elements for one or more cycles using various executor framework mechanisms. And you can see this cartoon I show here on the right-hand side that shows you can have an input source or input sources, one for each input cycle, and they basically feed tasks into the appropriate threading mechanism, in order to get the job done. This type of an approach is particularly useful for so-called embarrassingly parallel computations. That's where there are little or no dependencies between the tasks that are run. And in this case, there are no dependencies. They just all run separately. And the example I always like to use here is a washer, a laundromat with a bunch of washers, or in the laundromat with a bunch of dryers, and all the washers and dryers can run in parallel without having to worry about coordinating, other than the fact you probably need to finish your wash before you can dry it. There's another thing that I want to get across here that's really important called commonality and variability. And that's a very important set of themes when you're designing frameworks like the TaskGang framework. And you can learn more about commonality and variability at this link at my website at Vanderbilt. The framework itself supports commonality. What does that mean? It means it's got a bunch of methods that are reused by the framework and by applications that customize the framework. And it's also got a bunch of common fields, or so-called data members, depending on whether you're a C++ or Java person. And so these are ways of being able to have the commonality so that everybody has the ability to leverage these particular methods. And we'll see here that things like the barrier TaskGang and the image TaskGang applications, we talk about image TaskGang, we'll talk about barrier TaskGang in a future lesson to show off the barrier synchronization mechanisms in Java. These all reuse all this stuff. So we put this into a generic framework, and then we can leverage it in other contexts. Then there's also a bunch of common algorithms and control flow mechanisms. For example, there's a run method that is a template method from the Gang of Four book, the template method pattern, that defines the entry point into a TaskGang. So when you want to run the TaskGang, as you saw when we ran the driver program in the previous part of this lesson, it does a set of things. It gets the next input, it makes that the input, it initiates the TaskGang on the input size, and then it waits for all the tasks to be done. Now, you can actually customize this to do other things, but that's the default behavior of the template method. Remember, a template method is a pattern that defines an algorithm and then leaves it up to the subclasses to override different steps in the algorithm. There's another method called makeTask, which is a factory method that creates a runnable. And this is often used to run concurrently. We often create runnables that will run concurrently. And this, of course, implements the good old factory method pattern from the Gang of Four book. And you can see it's also got a bit of template method here too, because you get the input and you process the input, and then you call task done. But I'm primarily focusing on this as a factor method, something that makes something. There's another method called advanced task to next cycle, which controls whether or not we're doing one-shot processing, which means we just run one time for all the initial input, or whether we run the first time on the initial set of input, and then we do another cycle for the next set of input, and then maybe another cycle for the next set of input, and so on and so forth. By default, we don't do cycles. We just do it one time. So the default is just a one-shot operation. Then we also define an atomic long that's used to increment and read the current cycle. So we've got an atomic long and some methods to manage it. And this keeps track of the cycle count, which is useful for debugging. Now, those are some of the common things. There's also a bunch of stuff that must be customized by subclasses to support variability. And that's where things get interesting. So one thing that varies is, where does the data come from? And we have a couple of methods, a setter and getter method, that will set where the input comes from and then get the input. And so you can do these things in order to be able to get the input and do stuff with it. So that's stored as a list of elements that are generic of type E. And they can come from different places. They can come from files, they can come from strings, they can come from network connections, et cetera, et cetera, et cetera. And the framework doesn't care where the data comes from. It just knows that it gets it. Another variability is how many cycles to run. And to do this, we have a pair of methods, get next input, which will return the next input if there is any, or null if there's nothing left, in which case we'll bail out. And there's another method called advanced task to next cycle, which might or might not return true depending on whether there's more cycles to run. So you can use these two methods to give you either one-shot or cyclic behaviors. Something very important in the TaskGang, surprise, surprise, is how to structure threading and synchronization. And you can see here that we've got 5 different methods. We've got the initiate TaskGang, the set executor, get executor, await task done, and task done hook methods. And the get and set executor determine what type of executor is going to be implemented. Notice it's completely generic by default. You can have a fixed type of executor with like a fixed thread pool or a cached thread pool or a work stealing pool, et cetera, et cetera. You can also determine what type of concurrency model you want to have. Do you want to have a thread pool versus a thread per input or thread per task implementation? And you can also define what kind of synchronizer you want. For example, you can have a cyclic barrier or a phaser or a countdown latch. These are the barrier synchronizers that Java supports that we'll be covering in more detail in upcoming lessons. Now, whenever you use the thread per input model, you need to make sure you use a cyclic barrier. Cyclic barrier needs thread per input, otherwise you'll end up with deadlock. Another variability is what processing to perform on each input element, and that's done through the process input hook method. And you can determine whether you want synchronous versus asynchronous processing. We'll see how that works when we take a look at the implementation subclasses of TaskGang. And this allows us to do very scalable concurrent processing using thread pools or even use virtual threads, as we'll show in some of the examples too. Something else you can do is there's this method called await task done, which is how the main thread waits for all the tasks in the gang to complete when they're all finished. And this can be done through various means like join or countdown latches and so on. So those are basically the main methods in the TaskGang framework. So what we're going to now is we're going to go take a quick look at the TaskGang class. So here we are in the TaskGang class. You can see that this is the class that's an abstract class that defines a framework to spawn and run a gang of tasks that concurrently process input from a generic list of elements of type E for one or more cycles. And you can see here that TaskGang implements runnable. So it's got this run hook method, which is typically the way that you run the TaskGang. Now we've got a couple of several fields here. We have something that keeps track of where the input is located, which could come from wherever. It could come from a file. It could come from a network. It could come from strings. We have our executor, which will be used to submit runnables to run in a thread pool or some other kind of concurrency mechanism. We have an atomic long that keeps track of which cycle we're currently at. If we're doing cyclic processing or even just a one shot, it'll just have a count of 1. We have a method that returns the list to use as input. That you can see just returns the list here, just a nice little wrapper around that. We've also got a nice little setter method to set where the input comes from. We have executors for setting and getting, and you can see that they just set the executor and get the executor. We have a method that increments the cycle count by 1 and returns the current incremented value. We have something that returns the current cycle value without incrementing it. We have a method that will get the next input. This is an abstract method, so this needs to be filled in by a subclass. We'll take a look at that. There's also an initiate hook, which is a no-op by default. It doesn't have to be overridden, but it can be useful. We'll see how it gets used in some of the examples later. We have another hook method that's abstract called initiate TaskGang. That must be overridden by the subclasses, and it kind of starts off the concurrent processing typically. We'll see that used here shortly. We have advanced task to next cycle, which by default returns false. And that means that we only have a one-shot behavior unless we override that. We also have the await tasks done method, which has got to be overridden by subclasses that's used as an exit barrier to wait for the gang of tasks to be done with what they're supposed to do. And we have a task done method, which is also just a no-op. And this is called when a task is done. You can do the various things with this method. One thing you can do is just decrement a count for some kind of barrier to make sure that everybody's completed their cycle before whoever's waiting for it continues. You can also throw the index out of bounds exception if an item has been removed. We don't use that behavior here, but when we talk in an upcoming lesson series on the barrier TaskGang and Java's barrier synchronizers, we'll see how we use the index out of bound exception in a very clever way. There's yet another abstract method called process input that actually does the work, and if all goes well, it returns true. If it returns false, that means that the background task needs to stop running, basically by falling off the end. And this has to be overridden by subclasses. Here is the run template method that is going to essentially start the ball rolling. You can see we get the next input. Using our getNextInput hook method, we set the current input to be that returned value. If it's non-null, we call up to the initiate TaskGang hook method, passing in the number of tasks in the gang to be initiated, to be started. And then the run method just calls a wait task done. And that will essentially typically block or logically or virtually block the culling thread. And it'll then only complete once all the processing is finished in that gang concurrently. And then down here, we have one final method. This is the factor method called make task. And you can see that this returns a runnable task that will take the index that's passed in. So you pass in an index, and we go ahead and we look up in the input list that item. We get the item associated with that index, and then we're going to process that element. And if it's successful, then we say the task is done. So if we return true, then it means we're finished with this stuff. Otherwise, something has gone wrong, and we probably should have thrown an exception or something to bail out. If the index out of bounds exception is thrown, we just ignore it. That's used as an indication that the input size has changed between this run and another run. So those are all the methods that we define in the TaskGang framework. You can see this is a wonderful example of commonality and variability analysis at work, because some things are common, like all these methods and these fields, and some things can vary, and the things that vary are the things that can be overridden. And almost everything here can be overridden. I don't think there's any final methods at all, but some of these things must be overridden. And we'll see when we take a look at some upcoming subclasses from TaskGang, how the overriding is used in order to implement different concurrency models.